Okay. Hello everyone, my name is Rafael Ramirez and I would like to welcome you to the webinar Finite Element Modeling and Structural Analysis of the Church of São Miguel de Refojos. This project was developed within an international academic program named Advanced Masters in Structural Analysis of Monuments and Historical Constructions, and it is part of my final master thesis with the supervision of Paulo Lorenzo and Nuno Mendes. Okay, let's go. This presentation will be divided into 4 main blocks, and they are organized as follows. In the introduction, I will describe the case study and some important aspects of the building. In the second part, we will deal with the construction of the 3D finite element model using FX Plus for Diana. In the third block, we will see how to perform different kinds of structural analysis using Diana, and we will have a look at some relevant results that we obtained. And finally, in the last block, will consist in the conclusions and further studies that we can do with this work. Okay, so the case study is located in Cabeceiras de Basto, which is a town placed in the north of Portugal. The monastery that we can see in the pictures was founded in the 12th century by the Benedictine order, and it was located in a strategic place near a water stream. The building underwent several periods of flourishing and decadence until getting to our time. The church within the monastery, which will be the focus of our study, is the most relevant part of the complex, and its current aspect is a consequence of the works carried out during the 17th and 18th century when it was renovated in a Baroque style. The church has a Latin cross plan with a nave, transept and chancel, and it follows a classical east-west orientation. The external volume of the church is about 60 meters long and 24 meters width, and the interior height is about 18 meters in the nave and 16 in the chancel. The crossing is covered by a dome supported by pendentives, and in turn the dome is made up by a drum, a cupola, and a lantern on top. So the highest point of the church is approximately 35 meters above the floor. The main facade has 2 bell towers with quadrangular plan, and they are about 40 meters high, so these are the highest points of the whole building. Now inside of the church, on top of the main entrance, the choir loft is supported by a rear vault. The nave has adjacent bodies on both sides with smaller dimensions, and the ceiling is made by a barrel vault. In the center of the transept, the crossing is surrounded by 4 arches supporting the dome, and the ceiling again is made by a barrel vault. The transept also connects with the lateral chapel located outside the main body of the church. And now this final part. The final part is the chancel, made up by a presbytery with the main altar, and it also has lateral annexes, in this case in a lower level in relation to the floor of the church. The nave, transepts, and chancel are covered by gable roofs with ceramic tiles, and the structure of that roof on top of the nave is the only one accessible. And we could see in the inspections that it consists of timber trusses oriented in the shortest direction. During the last years, several inspection and diagnosis works were carried out in order to assess the general state of the building and to get to know some materials and mechanical properties. So the creation of our model is going to be based on these previous works, which will work as a reference and as a validation of the quality of our model. Now, before starting any model, it is really important to know what we want to achieve and how we should proceed, depending on the main features of our building, computational capacity, etc. The approach we choose will have influence in the overall quality and the results and the time needed to produce it. In our case, the main objective of the finite element model was to evaluate the structural behavior of the church in 2 different parts. Identify, on one side, the main causes of the existing damage, and on the other side, assess the seismic performance of the structure. Therefore, considering the main characteristics of our case, it was decided to build a macro model with 3D element solids and shells and beams in small proportion. So we would, from the whole complex, we would consider the main volume of the church with the nave, transept, crossing and chancel, and the facade with the towers, as well as the annexed parts and one on the other side of the nave and the chancel. Finally, the stiffness of the adjacent parts of the monastery would be included in the model as springs. For the analysis, the loads that would be considered were gravitational loads, mainly self-weight because of their own structure, the roof and the infill over the vaults, and then finally horizontal loading proportional to the mass for the seismic assessment. As boundary condition, we would consider two different models, one with pin nodes at the base, so fixed connections, and another one with interface elements that would represent the soil structure interaction. Finally, before starting, we have to be sure that our units are going to be consistent all the way through. So, now we get to the modeling part. There are different procedures in order to create a base geometry for the finite element model. We can, for example, import the basic geometry to FX and do Boolean operations to create the model, the solid model. We can create the solid model completely in FX, and in our case, which is more convenient maybe for complex 3D structures, we are going to import the whole 3D geometry from a CAD program to FX. In order to do that, when we open FX, we have to go to File, Import, Advanced Geometry, and IGES, and then by default. However, here the important part is how we created the model in the CAD program. I would recommend you, from my experience, to set the units precision to the maximum, checks, as I said before, that the units are consistent, place the origin of coordinates in a point that we can recognize later, and then organize CAD by material and properties. It is by the materials that we are going to use later and the properties, both material properties and elements. Then finally, we have to make sure that the final scope of the work is to create a model which can be studied easily. So some simplification must be done. For example, this avoid small distances would be one of them, because at the end that would require a mesh refinement, and that would increase the time need for the calculation. If we continue the whole process, we would have this. While we are importing the different blocks of the geometries, I would recommend you to group them into geometry sets. That will help with the visualization, because it allows you to show or hide specific sets that will be useful later for the meshing. So at the end of the import process, we should have something like this, where we can see the different parts and different colors, and we can identify the beams of the roof, the vaults that will be made with shell elements, and the whole system of 3D elements in gray. Now we get to an important part, which is the connection between the geometries. A proper connection is paramount in order to create a good mesh later and get representative results without any mistake. I will explain you some aspects to take into account according to the different types of elements and how are they touching each other. So we will see connections between solids, connections between solid and surfaces, and connections between solid and curves. Most of the time, the connections between elements of the same type are not a problem, but sometimes the connections between different type of geometries are more complex, but we will see. I would recommend you again to use all the possible Boolean operations in the CAD program originally. If not, if you are not comfortable or if you prefer to use it, it's always possible to use it directly in FX. So, connections between solids. They are easy, and the only thing we have to do is go to solid and Boolean cut. we have to check the Boolean master and then the Boolean tools. We should uncheck here the delete tools, because if not, it's going to take away those. We can use this operation everywhere, and we would be sure that all the edges between solids are represented in the adjacent solid. Here, for example, now we have here the edges. The second type of connection is between solid and surface, and for this we have to imprint the surface into the solid on this face of the solid. So imagine that we want to imprint these bolts into this wall, this solid here. We would select the wall, we would then select the face we want to imprint the object on, and we finally would select the curve. We would click OK, and we would have it. And then the last one would be solid and curve connection. In order to break the solid when we get a point, we can select the solid, select the edge, select the points, and then we would have the edge of the solid divided into those parts. Okay. Now we get to the second phase. Different materials were identified according to the inspection works: brick masonry for the walls, granite ashlar masonry for the thinner walls, and 3-leaf masonry walls for the main thick elements. In addition, auxiliary granite stone were considered for lintels, and the roof structure was characterized as timber. Initially, the mechanical properties were estimated based on literature, such as the Italian code, or based on experimental tests for similar materials or cases. This block of masonry, brick, granite ashlar, and 3-leaf stone masonry, would be then considered to have nonlinear range for later analysis, while the timber and the granite stone will always be considered in the linear range. Additionally, we would prepare a model with soil structure interaction, and we would represent the foundations as interfaces. And after some calibrations, we would get to this model where we have a deep sound foundation and a deep foundation with soil loss, with less stiffness. Okay. Now, before the discretization, we need to establish the type of elements for the mesh. And in our case, the type of elements were chosen in order to make the meshing process easier and to guarantee accurate results at acceptable computational costs, let's say. So these are the solids, the type of elements that we used to mesh the solids. The 4-node, 3-side isoparametric tetrahedron element. These here are the ones that we use for the shell elements, 3-node triangular isoparametric curved shell elements. And then these 3 of the blocks are lesser important elements. We use them for the truss, for the springs that would represent the adjacent parts of the monastery, and finally for the interface that would be used in a lecture model. And now, once we have the geometry and we have defined theoretically the material and the properties, we would create those materials and apply those properties. So the first step is to create the material, and we can see that we have different options. In our case, we would use these 3 types: isotropic, interface, and dummy for the springs. So the only thing we have to do is go to Analysis, Material, Create, select the type, fill the data, and apply. Once we have the whole list, we can go to the next step, which would be define the properties. In our case, we would have 3D, 2D, 1D, 0D, and interfaces. 3D would be used for the solid elements, 2D for the shell for the bolts, 1D for the beams, 0D for the springs, and interface for the solid structure interaction. Again, we have to go to Analysis, Property, Create, and then select the type of property we want to create and fill the data. This is going to be important for later, and is an advice that I can give you. When we define the materials, we can also include data ID and data name. I would recommend you to create one data ID for the materials and properties that would later have some, for example, nonlinear behavior, because to apply some element data to those materials with different ID is going to be easier. And it's really easy just to put here one number and define them. So I would recommend you to do this in the first step of the process. Now, for the example of how to mesh, we are going to take one part of the church and see how can we proceed with the different meshing options. This part, we checked before that everything was properly connected, but in any case we will see later how to check that actually our conditions between the solids and the surfaces, or the solids and the beams, are okay. Well done. So for this type of mesh with solid elements, it is important to define enough elements through the thickness of each wall, for example, in this case, because that would be a compromise between the time consumption of the analysis and the accuracy of the results. In our case, we decided to have at least 3 elements along the thickness, so we would have accurate stiffness, or accurate results according to stiffness, and enough integration points through the elements. So I would recommend you to start from the smaller or thinner elements to the bigger ones or thicker ones, because in that way Diana, or in this case FX, sorry, is going to automatically detect the nodes. So the connection between the thinner parts and the thicker parts would be more refined if we do first the thin one. We will see that now in the example. Let's start then with the shell elements. And in order to mesh a shell, you can go to Mesh, Automap Mesh, Automesh Face. You would have to select these faces, and then in here indicate the element size. In our case, we decided to put 0.3, 30 centimeters. Select the property, name the mesh head. You can either name them in the beginning and then apply this mesh to the mesh head, or you can create the mesh head right now. You can here with this button, you can pre-visualize where the nodes are going to be in the edges, and then you can click apply. So we would have, in this case, this discretization of the volts, and we can proceed to the next one. Every time that we deal with a combination of mesh between shell elements and solid elements, we have to assure that the nodes are going to be connected. So it's not only that we have to imprint the line on the geometry, is that also we have to tell the solid how many nodes we are going to have along the edge. In order to do this, we have different options to indicate the mesh size. In this case, we are going to use mesh size control along the edge, and then we will indicate the mesh size, in this case the same size as the one that we use for the discretization of the shells for the volts. I would recommend you to put a name here to identify them, and then in this button we can see how it's going to be divided later. We can apply, and then it will be already noted in the system that when we mesh the solid, it has to have these nodes in this location. Now, To mesh the solids is similar to meshing the shells. We go to mesh, auto mesh solid. We will select the solid, indicate the element size, property, name of the mesh set, and we can apply. When we create this solid, here we can see that the connection between the solid and the vault, the shell elements, is going to be acceptable because we defined it before. And we can see here how the mesh, in this case it was 13 centimeters, how the mesh gets more refined when we get to the shell ones, which was just 30 centimeters. Now we continue, and we will see how now with a different mesh size, when we get to the connections between the solids, also the mesh will adapt to automatically join the previous one. Here we can see how the distribution is regular, and here it changes. And we will see later how to check that actually every connection is properly done. Now finally, for the beam elements, we have to do the same, assure that the connection between the line elements and the solids is going to be properly done. Or in this case also it could be between the beam elements and the surface elements. So we go to mesh, size control, and again along size, and in this case we can use the other option, number of divisions, since we know that there are 4 divisions here. We click and preview, and we see that this is going to be the discretization of the mesh when we create the beam. So we can go for the creation of the beam, element to mesh, auto mesh edge. We select the edges. We indicate, as we did before, the interval length, in this case 0.5, just to check that in here where we have the connection between solid and edge, we will effectively see how the mesh adapts to the size that we defined. We have to indicate the property, again the mesh set, and this would be the previsualization. So we click apply, and then to check that when we can have cross sections for beams, circular or like squares, so that would be no problem. But if we have rectangles, we have to be sure that actually they are oriented in the proper direction. So this is a way to check it. We can go to property here in the pre-works tree, select 1D properties, and show section in the one that we are interested. In the show section option, we will have this view, and in case that some part or some beam is not oriented properly, we could come here to mesh, change element parameters, and then with 1D selected, select the beams that we want to change and change the orientation here and apply. That in case that we have to indeed change something. Okay, so if we follow this, at the end we would have a huge mesh. And how to control easily that everything is well done. Okay, so there's here an option. Once we have created the whole stuff, we can go to mesh, and here in node, merge. This can be a tool to use, but also like a tool just to check that everything is done properly. If we select the nodes of the mesh created, we can use this command here, put a tolerance, a really low tolerance, and find. So the program will, if everything is correct, the program will tell you this here. There is no node in the assigned tolerance distance. We can check this iteratively to put 1 millimeter and then 1 centimeter, so go up and check that everything, all the nodes are together. That means if there is no node with this tolerance, is that everything is perfectly joined together. If there are nodes that are not connected, they are going to appear in red, so you will see that something is wrong, and you will be able to solve the problem. Another important option in this case is the check quality of the mesh. This is something that has to do with the previous step that I told you before, the geometry. The geometry should be such that is able to adapt the mesh with good quality. That means that smaller distance or small triangles or really thin corners, we should try to avoid them, because in here, when we check the mesh quality with aspect ratio, we would have this red or orange colors, like really poor quality elements that can compromise the calculation process. So this is an easy tool just to check that in general we don't have poor quality elements in the mesh. Then again, with the discretization, we will go to the next step. There is another kind of element, and it is the springs. The springs, we said that they were used to represent the stiffness of the adjacent parts of the monastery. So in here we have a wall, in here we have a wall, and the cloister, the horizontal slab of the cloister, they would represent a stiffness in this case. So they would change the mode shapes, for example, or in the case of the later pushover analysis, the capacity curves. So this is a practical thing to do when you have influence of adjacent buildings, but you don't have enough computational capacity or time just to model everything, so you can try to represent them as an adjacent stiffness with this. So in this case, to create springs, we can go, I would recommend you to create the mesh sheds before. Select the nodes and apply to those mesh sheds, and then isolate the mesh sheds and create the springs with this command. Create one node element, and then you would select the nodes, apply the property, add to the mesh shed that you created before, and apply. And finally you would have this kind of representation where you see the different nodes with this symbol that represents the springs. The last type of element that we are going to produce is the interface element to represent the interaction between soil and structure. So the foundation and the soil underneath the base. This is going to be used in a later model that is going to be defined as model 2, because it has the influence of the soil in the behavior. In order to create an interface, we can have different procedures, but I'm going to explain you this one here, which seems to be quite simple. We can go to mesh. We have to have a frontal view, for example. We can go to mesh, protrude mesh, extrude, this option here, if face to 3D, and then select the element at the base, these faces here of the solids. We will define a direction for the extrusion, vertical one. In here set a number like -1, -2 meters, and one division. We would apply any property, because we will change it later, and mesh it as we want. Apply, and we would have created this, a new set of elements extruded from the base. In this step we will convert those elements into the interfaces. So we can go to mesh, element, create interface element, or this button here, select plane, and method convert elements. So we would select the elements we created before and the nodes that were originally the base of the structure. Assign the interface property we created before, and then apply. And we would have this, where we have the interface. After the elements, we will define now the boundary conditions. In our case, we would have just pin connections as constraints. So we can come here to analysis, boundary condition set, just name it and add. And then to properly put the constraint, we can come to boundary conditions, we did before. Analysis, boundary conditions, constraint, and then we check here. In the case of solid elements, to put pin connections would actually assure that the base is fixed, because it will not let rotation. So if we do that, we apply, and we will see this, that all the nodes at the base have these 3 degrees of freedom representing translations blocked. One important aspect when we deal with different kind of elements too is the degree of freedom compatibility, because it can produce problems in later hard computations. Sometimes they do not produce any kind of error, but they can. So in case we deal with different types of degrees of freedom for different elements, the nodes that they share, I would recommend you to do this process of assuring that every node is behaving in the same way. So for example, when we have beam elements and solid elements, the nodes cannot rotate, so they are defined with 3 degrees of freedom in each node. But beams can rotate. So what happens when a node belonging to a beam, or part of the element belonging to the beam, can rotate and the other not? We can have a mathematical contradiction. So in order to block the degrees of freedom of the beams and get the behavior as the solids, we can go to Analysis, Beam and Release, select the elements, and then block every rotation. So we would have here 4, 5, and 6 degrees of freedom. The ones representing rotations are blocked. So these nodes will not rotate, and then they would be compatible. Again, this can represent a problem or not, but I will suggest to do this process because it's easy and doesn't take so much time, and we will assure more accurate result, or at least no mistakes. So at the end of it, we would have this model perfectly meshed with every node connected to each other, and the last step is define the loads. In our case, we would have, for the first analysis, just gravitational loads. The body force represents the weight of the own elements. We would also include linear distributed loads on top of the trusses to represent the roof that we are not considering in the model. And finally, we would include also a pressure load on top of the lateral sides of the vaults in order to represent the infill that, again, we are not representing in geometry in the model. So in order to apply the self-weight, we go to Analysis Load, Body Force, we create the load set, and we check gravity in the third direction, and we put -10 or minus 9.8, 9.81. Okay, and this step would assure that the self-weight, the automatic self-weight, is activated. As we said before, we also applied a linear distributed load on top of the trusses representing the roof. So we create the load set as roof, and in here we can select the element, select the direction, and in case that it's linear distributed, so we put here the same value. Well, we also can define it as a function, changing. We have different possibilities. And finally, we would get to the pressure on top of the lateral parts of the vaults that represent the infill that we are not producing graphically. So in order to produce a pressure, I know this way. We can use this way. Load set infill that we created before. Select object type and surface, and we are seeing the geometry of the vault. We select it, we apply the direction, and we apply here, in this case, because it's a simplification of a triangular pressure, we create a function which needs, in this case we have this y direction across the volt and x direction in the direction of the extrusion of the volt. So we would define a point A where the load is going to have a value 1, and a point B where the load is going to have a value 0. So we would have a triangular pressure. This is a simplification of the infill load. And then if we can either create that function before and apply it now, or we can create it here right away. So after we put the value, we have to go to pre-works tree, load, we select the load set, pressure surface, we right click on it and transfer to the finite element. That means that we created the load on top of a geometry element, but we have to effectively apply it to the mesh. So this process is just to apply it to the mesh elements. And after this, we are ready to start running the analysis. In our case, we perform different types of analysis. We created, as we said before, this model 1 with a fixed base. So every node at the base was pinned. And this model 2 with soil structure interaction. So the nodes at the base would have an interface with some stiffness representing the foundation and the soil underneath the building. The first step is always linear static analysis and check that everything is correct. The vertical reaction should be the weight of the building, the displacement should be logical, and the stresses at the base should be as expected for this type of building. After that check, we can go to the model analysis, which would give us the natural frequencies and the mode shapes. In our case, we had from the previous experimental test dynamic properties, dynamic identification tests. So we used the model analysis in order to check that our model was close to the real behavior of the structure. Doing that, we calibrated the model and we got updated mechanical properties and a model that could be used for later analysis. After that set of analysis, which consists in isotropic materials in our case and linear range, we define nonlinear properties for the materials and start nonlinear static analysis. We performed two different kinds of analysis in terms of direction. So we did one analysis for the self-weight of the structure, and then we increased the load vertically to check the vertical capacity of the structure. And on the other hand, we load the structure horizontally in a monotonic way. So nonlinear static analysis, or also pushover in different directions. Minus X is missing here because it was against the springs, and also we have to take into account that the springs can represent some inconsistencies in when we have analysis of this type. And also, like, if we push against the building, it's not the most vulnerable direction, so we can maybe skip that in pursuit of simplification and time saving. So with this last analysis, we would get cracking patterns and seismic vulnerability assessment. In order to calculate, we no longer use FX, we go to Diana. And in order to do that, in FX, we export a pre-neutral file, and in Diana, we import it. When we open it, before anything, we can do one thing, that because of the way we defined our model, we had 3 load sets, but actually all of them represent self-weight. One is the self-weight itself was the body force, was because of the elements, And the roof and the infill was because some elements that actually were not presented in the structure. So we can go to combination, edit combinations. We can put 1 and all of these. These are multipliers of the loads. So in case we also have to do an analysis with different multipliers, we can also here change that here. And we can erase the other 2 combinations, so we would only have 1. When we have that, we can go to the Analysis tab, add analysis, and in this case we're going to do the linear static analysis as we defined before, the first step. We create an analysis command and add structural linear static. In here, we change the output to get Midas effects for Diana, so we will have the results produced in Midas in order to see it. And we would check in here displacement, strains, and stress as we want them, which is displacement at the nodes, strains, and stresses at the integration points. So following this process, we can define the output as we want to. Also, I would recommend you to, every time that you define an analysis, you can save that analysis or in the future load it, so you don't have to define this every time. You just can have one reference file where you go always. Once we have produced the linear static results, we can come to effects, and then in the results file, right click here, add the analysis that we have produced, this DPP file, and import. If we would have reinforcements, we should put them here in the other tab. And then when we analyze the results, we can have this as an information, vertical displacement, stress at the base. For model 1 and for model 2, we can check actually how the interface influences the behavior. So in this first model, we have really symmetric distribution of the displacements, with both towers moving the same. And in this one that has the southern part of the church with less stiff interface, we can see that this tower actually moves more. When we check the results of the stresses at the base, we also get that they are different, and this is as expected because they were like, it's meaning that the interface and the models are working properly. So the linear static analysis is to check that thing, have an idea of displacements, stresses, and check that actually the model is working properly. Then we can go to the next analysis, which is the model analysis, eigenvalue analysis, and we would again load the analysis as before, select the number of eigenfrequencies that we want to, and in the device again select Midas for FX. In our case, I'm presenting here the results for the model 1, so the one with the fixed space. These are the 3 modes that we identified. They were according to their similarity with respect to the experimental ones that we can see down here. In general, the frequencies obtained with the numerical analysis were lower, so that means that our model is not stiff enough, and so properties should be modified to obtain more accurate results. We can do that manually, but we used a calibration procedure based on the Douglas-Reid method that uses an optimization algorithm to minimize the difference between the experimental and the numerical responses. Okay, in our case, what we used to calibrate the frequencies was the modulus of elasticity of the materials, and we will use them as a variable to calibrate. The masonry materials, the brick masonry, stone, 3-leaf stone masonry, and granite and sand masonry were used as variables, and the reference upper and lower values of these 3 groups were selected from the range given by the Italian code. So in this process, different eigenvalue analyses were performed, changing just one of these properties at each time, and a set of frequencies was obtained for the selected modes for each case. After the calibration and optimization, the final updated frequencies were obtained together with the recalculated values for the initial variables. So we would have 3 new modes with less error, and the variables that we use, the property for the materials, were logical within the range that we saw, that we were establishing. So they make sense, and we can conclude that we have a calibrated model that can be used for later analysis because it properly represents the behavior of the structure. The mode shapes were not included in the calibration process, but the modes that we calibrated were actually chosen because of the similarity in the mode shape. And also we check that actually the mode shape was consistent using the model assurance criterion. And in this case it also showed a good correlation, so we can conclude again that the model is properly defined. In any case, this MAC, model assurance criterion, consists in a numerical comparison of the eigenvectors for the dynamic identification test in our case and the numerical results. So the experimental and the numerical results. This MAC value ranges from 0 to 1, meaning that 0 is absent of correlation, so it has nothing to do, or 1 when it's perfect match between the mode shapes. In our case we have 86, 96, 94, so really good correlation between the mode shapes. And in this process, just to, as a note, the eigenvectors have to be normalized. So the maximum value of the model displacement is equal to 1. But in case, what we, the interesting part of this is how to, actually it is used to validate the model, but in our case it serves as an excuse to learn how to take tabulated values in Diana. In this case we have to check. We have as an information, as an input, the accelerometers, the eigenvectors given by the accelerometers with the corresponding directions. And we want to have the results equivalent for our nodes that would represent actually the position of those accelerometers. So we have to first check which nodes we want to extract information from, and then rerun the eigenvalue analysis, but in this case in here device with tabulated and the nodes that we want to here. It will generate a table that we can read, and then we can check, in this case, the MAC values for the mode shapes. Okay. Now we go to the next set of analysis that are the nonlinear analysis. In order to, first of all, in order to perform a nonlinear analysis, we have to define nonlinear properties for the material. As we said before, in our case, the 3 main groups of masonry materials were considered to abandon the linear range at some point and behave in a nonlinear range. So in order to change that thing, we can come here in Diana to materials, edit material, and add a class and a material model. In here you can define different material models depending on the type of analysis you're going to run or the considerations that you're having for your materials. Also, it is advisable that if we have shell elements, or if we have elements that by default they have 1 integration point along the thickness, we should come here and for the nonlinear analysis increase the number of integration points. In this case, we can, if you work with the previous version, it was this command, or if you work with the new versions, it is this command. So now the final part, we can choose to perform analysis with the mesh editor or interactive environment of Diana, or we can also, maybe it's more convenient for heavy models, complex models, to use the command box. For the command box, what we need is the DAT file that we can produce in Diana, as is explained here, file export model, set this to maximum and save as that, and that would create the model but in a numerical form. And we would need the data file, the command file, and just in case a Philos file that would represent the following of the analysis by the program. So if we want to check, for example, the self-weight, we would need to define in the data file all the directions that we will use later. For example, for the pushover analysis, all of the directions that we are going to implement later, they have to appear from the moment zero of the nonlinear analysis, because we are going to concatenate one analysis to the other. So we can see here that we have plus x plus y plus z minus z, that is the gravity one, and minus y, which is one of them that we are going to use for the pushover. Then if we search in the table, we will get to materials, and we have to check that actually the material properties, the nonlinear properties, are included. Also in the future we can include the nonlinear properties in this part here. We can check also the data that is included. In this case it was with Diana 9.6 and this command in the Diana 10 in Diana 10 or 10.1 is just thinte 5 would be. And then we would have this last part with the cases. We would have, we had before, in this case we did not erase case 2 and case 3, so we have the self-weight, the roof and the infill as case 1, case 2 and case 3. And then we have case 4, which is the pushover in x direction, the case 5, which is the pushover in y direction, and the case 6, which is the pushover in minus y direction. This is regarding the data file. In the command file, it's in here on the other side, we can define also different steps, different procedures, how to do stuff, or increase or change things in the command file, or include things or delete things, or for example define also the output file that we want to. In this case we start for the self-weight, so we include load 1, which represents, as we said before, the self-weight with the other roof and infill included, and the size is going to be 0.1 in 10 steps. So at the end we will have a step size of 1, which represents the self-weight itself of the building. In our case, the energy, the criteria for the convergence was energy of this value. For example, here we use the Newton modifier, but again, once we have this type of file, it is easy to change values, properties, step sizes, convergence criteria. That is really useful for complex models. When you get to the convergence stuff, sometimes it does not converge, so you have to again change that. Now, this is how to use the command box. You have to input the folder, cd space and folder, enter, and then you can have to write Diana space -m space name of the dat file point dat, name of the command file point DCF, sorry, and enter, and it will create a Philos file that represents the following of the program, of the whole procedure of the calculation. When we get to the final step of the self-weight, we will have a file that is called Diana FF or Diana 10 FF if you save the step. You have to copy that file because in the future you are going to use it. For example, when you are, if you push in the horizontal direction, you need the last step of the self-weight, and you would push from that moment on. Okay, so once we have done, we can, as we explained before, change the load direction, the step size, perform the analysis, and at the end we will get results of this type. For example, for the model 2, the one with the interface elements, for the self-weight we will have a distribution of damage like this, so crack, or indication of weaker zones. We will have vertical displacements as we did before, and we also have distribution of stresses. For the vertical overloading, so when we monotonically increase the weight of the structure, we will have results like this. again, to check these capacity curves, we used the 2 points with the highest displacements with tabulated results as we did before, or in effects creating tables. And we checked that the vertical load factor, the maximum one, is like around 1.8 its self-weight, and every jump of the curve, it represents some change in the global behavior of the structure, and in this case it represents actually the collapsing of the walls. Even if the structure can resist the global behavior of the structure, is able to resist more weight, some parts can have local damage. Also, we can have the crack patterns for the end of the capacity curve that can be associated with the mechanism of collapse. Finally, we can check also, like from the pushover, the capacity of the seismic vulnerability of the building. And in this case, we get that the most vulnerable direction is Y, and it has a maximum base shear factor of 0.89. This value can be directly compared with the one defined by the codes, that in the case of Portugal and the north of Portugal is 0.50 basic acceleration, and for type 1, and 0.8 for type 3, for type 2. So finally, we get to the conclusions. So what have we learned? We have seen different approaches and techniques to create and analyze a finite element model. We were able to calibrate the model, so now we have models which are representative of the real behavior of the structure and can be used for later analysis. We have checked the safety condition of the structure and with different scenarios, and it shows overall good behavior. In any case, we can always do better and more. So in our particular case for the church, further works could benefit from additional testing in situ, most of all regarding the soil structure interaction, and also numerically we could include other numerical approaches as time-dependent dynamic analysis, or different approaches also for the considerations of the adjacent parts or of the interaction between soil and structure. I hope everything was clear. I put here the references regarding different things that I was telling on the presentation. And well, I hope everything was clear, but in case you have doubts or in case you have any question or even recommendation, also is acceptable, and we have now time to answer questions. If there is something that needs more time, I would gladly answer you by mail to your doubts. Thank you very much for your attention, and I hope you liked it.